Our project demonstrates the daily phenomenon of watered-down drinks. How many times have you poured a nice tall glass of pop, dropped some cold ice cubes in it, but before you could drink it, your scattered brain reminded you about that important thing you needed to do right now? Finally, you get to take a luxurious sip of cold pop to only realize it's watered down and nasty, and you end up dumping it out. Chemical engineers can help find a solution to this everyday problem.
So Lana, how does putting ice in my water make it colder?
Well, Arjun, the driving force behind every heat transfer is the difference in temperature between the two things.
So in this case, it's the ice in the water.
Yeah, so there's a transfer of thermal energy from the water to the colder ice, which causes the ice to warm up and eventually melt.
Are there other factors that affect heat transfer?
Well, yeah, there's the heat transfer coefficient, which is the property of the substance, and there's also the area of the interface between the two substances.
So in this case, it's the surface area of the ice.
Exactly.
When we're considering convective heat transfer, we use Newton's law of cooling to define the rate of heat transfer. In our experiment, we use the same difference in temperature throughout. We also use the same materials to keep a constant convective heat transfer coefficient. All that remains is the surface area. The rate of heat transfer will only change with a change in surface area. Larger surface areas will result in faster melting. The different ice shapes have different surface areas and thus will have different melting times. Because we're using complex three-dimensional shapes, we had to approximate these surface areas. For the cube and truncated pyramid, these areas were found with simple geometry. For the fish and ice cream shape, the areas were found by lining the tray tightly with aluminum foil and then spreading the shapes out over graph paper. We then found the area from the graph paper.
In order to effectively understand how large of an impact surface area has on melting time, we designed an experiment that allowed for only the surface area of each ice shape to change. Our project required precision in every step along the way. In order to accomplish this, we first prepared 2 cups of water with 25 drops of blue food coloring. We measured exactly 10 milliliters of this mixture into each ice shape. Each would be submerged in 400 milliliters of water at 22 degrees Celsius. In order to ensure that each shape remained fully submerged, we froze them with a toothpick in the center. This toothpick was then punctured into the bottom of a styrofoam cup, which was firmly pressed into the glass containing 400 milliliters of water. The shapes were simultaneously placed into these glasses, at which point a timer was set in order to record the time it took for each to fully melt.
To keep our parameters as consistent as possible, we used an equal volume of water in each ice shape and in each glass respectively. We used the same temperature of water, and we tried to expose each cube equally to the air before submerging it into the water. Through our calculations, we found that the fish had the largest surface area, followed by the ice cream cone, the truncated square pyramid, and the cube. This surface area to volume ratio caused us to believe that the ice shapes would melt in the same order of largest surface area to smallest surface area.
While our results revealed that the average melting times followed our hypothesis, some individual trials strayed from our predictions.
This discrepancy between our hypothesis and the experimental results develops from the shape of the ice constantly and inconsistently changing while it melts. This makes it very difficult to model the effects of surface area on the melting time of ice.
So then, what can we do with this information?
Well, chemical engineers can design a more practical method for producing spherical ice.
But why spheres?
Because a sphere has a reduced surface area to volume ratio, which will reduce the heat transfer between the ice and the water, and that'll make your drinks stay tasty longer.
So I won't have to dump out my watery drinks and keep wasting money?
No, your drinks will stay tasty longer and you won't have to dump out your drinks.
Not only can chemical engineers design effective spherical ice cube trays, but they can also apply the principles used for this experiment in other ways. Adding fins to a process is one method used to efficiently transfer heat by introducing a larger surface area on which convection can occur. A larger surface area fin will produce a larger convective heat transfer rate, similar to how increasing the surface area of the ice shapes produced a larger rate. As an example, many grate heaters have fins to quickly heat up a room. Chemical engineers can improve this application by designing fins that have a larger surface area but don't take up a lot of space.